What if the sun suddenly disappeared? Close your eyes for a moment. Imagine you are standing outside on a clear morning, the warmth on your face, the light filtering through the atmosphere in that familiar golden way, the birds responding to it, the plants reaching toward it, your own body, calibrated over millions of years of evolution, responding to it. Now imagine that at this very instant, without warning, without cause, the sun simply ceases to exist. Not an explosion, not a gradual dimming, a disappearance, an absence where a star used to be. What happens next is not what most people expect, and the reason it is not what most people expect reveals something profound, something almost disturbing about the nature of reality itself, about how information travels through the universe, about the relationship between space and time and gravity, about what it means for something to exist at all. This is not a story about destruction, though destruction will come. This is a story about the architecture of the cosmos, about how the universe communicates with itself, and about how fragile and how extraordinary the arrangement of our small world truly is. Let us begin not with the sun's disappearance, but with a question that sounds simple and turns out to be anything but. What is the sun to us right now as we stand on the surface of the Earth? You might say it is a star, a ball of plasma, a fusion reactor. All of that is correct, but I want you to think about it differently. The sun to us is a source of three things simultaneously. It is a source of light, it is a source of heat, and it is a source of gravity. These three things feel connected, intertwined, as though they all arrive together as a package. And in ordinary experience, they do. But they are not the same thing. They do not travel the same way. They do not, in the deepest sense, obey the same rules. And when you understand the difference, the thought experiment of the sun's disappearance stops being a simple disaster scenario and becomes a window into some of the most profound physics ever discovered. Start with light. We know that light travels at approximately 300,000 kilometers per second. This is not just a number, it is one of the most fundamental constants in the universe. Nothing with mass can reach it. Information cannot exceed it. Causality itself is built around it. The speed of light is not simply how fast photons happen to travel. It is the speed limit of reality. Now, the average distance from the Earth to the Sun is approximately 150 million kilometers. Divide that distance by the speed of light, and you get approximately 8 minutes and 20 seconds. This means that when you look at the sun, you are not seeing the sun as it is right now. You are seeing the sun as it was 8 minutes and 20 seconds ago. The light reaching your eyes departed the sun's surface before your last cup of coffee. The sun you see is always a memory, a beautiful, life-giving memory, but a memory nonetheless. This delay is not a minor technical detail. It is a statement about the nature of observation and existence. There is no such thing as seeing something as it is at this moment, if that something is at a distance. Every observation is a message from the past. Every photograph of a distant galaxy is archaeology. The further something is, the older the light. The most distant objects we can observe are being seen as they were over 13 billion years ago, when the universe was in its infancy. We are, in a very real sense, looking at a cosmic fossil record every time we turn our telescopes to the sky. But let us return to our thought experiment. The sun disappears, suddenly, completely. At the moment it disappears, let us say it is midday for someone standing at a particular place on Earth. They are outside, they feel the warmth, they see the light, and they have absolutely no idea that the sun is gone. They will not know for 8 minutes and 20 seconds. For exactly that long, the light that had already left the sun before it disappeared continues to travel toward the Earth. It is already in transit, already crossing the void. It cannot be recalled. It has no knowledge of what has happened behind it. So for 8 minutes, the sky looks normal. The birds still sing, the plants still photosynthesize, children still play in the sunlight. And then, without any warning, the sky goes dark. Not gradually, not with a flicker. In one instant, the sun vanishes from the sky. The last photon has arrived, and then there is nothing. No twilight transition, because there is no source anymore. No final glow, because the light that had been on its way has finished its journey. Just darkness. But here is where the thought experiment becomes genuinely extraordinary, and this is the part that even people with some scientific background often get wrong. The question is, what about gravity? The Earth orbits the Sun because the Sun's gravity curves the fabric of space-time around it, and the Earth follows that curvature. This was Einstein's great revelation. Gravity is not a force transmitted across empty space like a signal. It is a curvature of space-time itself. The Sun's mass creates a kind of depression in the geometry of space, and the Earth, moving through that geometry, follows a curved path around it. This is the orbit. Now, when the Sun disappears, what happens to that curvature? Does the Earth immediately fly off in a straight line? Does the gravitational effect vanish at the same instant the light does? Or does it vanish 8 minutes later, along with the last photons? The answer, and this is the counterintuitive and deeply important part, is that gravitational effects, according to our best understanding of physics, travel at the speed of light. They do not travel faster. They do not travel instantaneously. Einstein's theory of general relativity, confirmed through decades of observation and experiment, predicts that changes in gravitational fields propagate through spacetime as waves, and those waves travel at exactly the speed of light. This was a theoretical prediction for most of the 20th century, and then, in September 2015, it was confirmed. The LIGO detector, a pair of extraordinarily sensitive instruments in Louisiana and Washington state, detected for the first time the ripple of space-time caused by two black holes merging over 1 billion light-years ago. Gravitational waves traveling at the speed of light arrived at our detectors and caused a disturbance so small it was almost incomprehensible to measure, a displacement smaller than 1/10,000th the width of a proton. But it was there, and it matched Einstein's predictions with breathtaking precision.
What this means for our thought experiment is this. When the Sun disappears, the gravitational disturbance created by that disappearance, the sudden change in the curvature of spacetime, propagates outward from the Sun's former location at the speed of light. For 8 minutes and 20 seconds, the Earth continues to orbit as if the Sun were still there. Because as far as the geometry of space-time around us is concerned, the Sun is still there. The curvature it created has not yet had time to change. The Earth, following the contours of space-time as it has always done, keeps moving in its orbit. And then, at the same moment that the last photon arrives and the sky goes dark, something else happens. The gravitational influence of the Sun reaches its endpoint. The curvature of space-time in our region begins to change. The Earth, no longer following a closed curved path, begins to move in a straight line. Or rather, it begins to follow whatever new geometry the absence of the Sun creates, which is very close to a flat, uncurved geometry. And a straight line in nearly flat space-time is simply a straight line through space. The Earth begins to drift away from where the Sun used to be. Think about what this means. For 8 minutes, we orbit a ghost. The Sun is already gone, but its gravitational handprint, impressed into the fabric of space-time, continues to guide us. We are held in place by the memory the universe is still carrying. This is not mystical. This is physics. But it is a physics that, when you sit with it, has a quality that transcends mere mathematics. It speaks to the way the universe stores and transmits information. The universe does not update instantly. It updates at the speed of light. And for 8 minutes, it has not yet received the news. Now let us walk through what happens to humanity and to the Earth in the hours, days, and years that follow. Not as a catalog of disaster, though disaster it is, but as a way of understanding how intricately and completely our existence is bound up with the existence of our star. First, the darkness, the immediate and most obvious change. The sun is gone. The sky is now what it would look like on any other dark night, except that it is the middle of what used to be the day. Stars become visible. The moon, which reflects sunlight and has no light of its own, goes dark as well, since there is no longer any sunlight to reflect. The planets similarly go dark. The universe that was hidden behind daylight is suddenly, completely visible. For a brief moment, if you were in a position to observe it, the sky would be spectacular. Every star we have ever wondered about, every constellation, visible simultaneously. But the cold comes quickly. The Earth's surface temperature is maintained by a constant input of solar energy. Remove that energy, and the surface begins to radiate its stored heat outward into space. Within a week, the average surface temperature of the Earth would drop below 0 degrees Celsius across most of the planet. Within a year, it would drop to around -70 degrees Celsius. Eventually, it would settle toward the temperature of the surrounding space, somewhere around -270 degrees Celsius, just a few degrees above absolute zero. The oceans would begin to freeze, not all at once, but progressively, from the surface down. The atmosphere itself, the thin layer of gas that makes all of this possible, would eventually begin to condense and solidify, the various gases in it liquefying and solidifying in the extreme cold.
Photosynthesis, the process by which plants convert sunlight into chemical energy, stops instantly. Plants begin to die. Within days, the base of almost every food chain on the surface of the planet has collapsed. The ecosystems that took hundreds of millions of years to build, the extraordinary web of interdependence that covers every continent and fills every ocean, begins to unravel. There are exceptions, and they are worth noting because they tell us something important about the resilience and creativity of life. Deep in the oceans, near hydrothermal vents, communities of organisms exist that do not depend on sunlight at all. They derive their energy from the chemical reactions between superheated water and the minerals in the ocean floor. These communities, built around chemosynthesis rather than photosynthesis, would survive. Not comfortably, not unchanged, but they would survive. Life, wherever it has found a foothold, clings to it. And there is another source of heat that is often overlooked in this scenario: the interior of the Earth itself. The Earth's core is extraordinarily hot, maintained by the decay of radioactive elements and the residual heat from the planet's formation. Geothermal energy reaches the surface through volcanoes and hot springs and geothermal vents. The amount of heat that arrives this way is a tiny fraction of what the sun provides, but it is not zero. In principle, a technologically sophisticated civilization, knowing this catastrophe was coming, might build habitats near geothermal sources, using that heat for warmth and energy. It would not be the civilization we know, but it would be life. It would be survival. The universe, even in its harshest configurations, leaves gaps for possibility. But we are getting ahead of ourselves. Let us return to the physics, because the departure of the sun creates consequences that extend far beyond the darkening and cooling of our world. The sun does not simply provide light and heat to the Earth. It is the gravitational anchor of the entire solar system. Every planet, every moon, every asteroid, every comet, every grain of dust that orbits the sun does so because of its gravitational influence. When that influence ends, the entire structure of the solar system, built and refined over 4.5 billion years, ceases to be a bound system. At the moment that the gravitational change propagates outward from the sun's former location, every object in the solar system that was in orbit around it begins to move in a straight line or very close to one. Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, Saturn, Uranus, Neptune, and the vast, distant Kuiper belt objects, all of them simultaneously released from their orbits, all heading in whatever direction they were moving at the moment of release. all diverging from the common center they once shared. The solar system, in a matter of months, begins to dissolve. Some of these objects will, over long timescales, pass near each other. Gravitational interactions between them, without the dominant anchor of the sun, will become chaotic in the technical sense. The word chaos here has a precise meaning in physics. It does not mean random. It means that the system is exquisitely sensitive to initial conditions, that small differences in position or velocity grow exponentially over time, making long-term prediction impossible. The planets, over millions of years, might collide with each other. They might settle into new stable configurations. They might be flung out of the solar neighborhood entirely, becoming rogue planets wandering through interstellar space. We cannot predict which. We can only know that the ordered, beautiful arrangement we have taken for granted, the arrangement that made our existence possible, is gone. The Earth, specifically, would be traveling at the speed it was moving in its orbit at the moment of the Sun's disappearance. That speed is approximately 30 kilometers per second relative to the Sun's former position. At that speed, the Earth would travel 1 astronomical unit, the distance from Earth to Sun, in about 58 days. In a year, it would be about 19 astronomical units from where the Sun used to be, somewhere around the orbit of Uranus in the old solar system. In 10,000 years, it would be a significant fraction of the distance to the nearest star. In 1,000,000 years, it would be somewhere in the deep interstellar medium, surrounded by nothing but the faint glow of distant stars and the cold of deep space. There is something extraordinary about imagining this journey. The Earth, a traveler, released from its ancient orbit, moving through the galaxy, carrying with it, frozen and dark, every mountain and ocean and fossil and human artifact and piece of music ever composed and mathematical proof ever derived. A silent archive of everything that life, over nearly 4 billion years, discovered about how to be alive in the universe. Moving through the dark between the stars. Finding, eventually, if it were fortunate in its trajectory, another star, another source of warmth and light. The probability of that encounter on any human timescale is essentially 0. On cosmological timescales over billions of years, the probability improves, but still remains very small. But the universe is patient in ways that are almost incomprehensible. Now, I want to draw your attention to something that this thought experiment reveals about the nature of scientific understanding itself. For most of human history, the relationship between gravity and the speed of light was not understood. Newton's theory of gravity, which dominated scientific thinking for over 200 years, described gravity as an instantaneous force. In Newton's framework, if the sun were to disappear, the Earth would instantly feel the absence. There would be no delay. The Earth would immediately begin to move in a straight line. This was not presented as a flaw in Newton's theory. It was simply how gravity was understood to work. And for almost all practical purposes, Newton's theory is extraordinarily accurate. The orbits of planets, the trajectories of comets, the behavior of tides, all of these are predicted with remarkable precision by Newton's equations. But Einstein recognized that instantaneous action at a distance was deeply inconsistent with the special theory of relativity, which he had published in 1905. Special relativity established that no information can travel faster than light. If gravity were instantaneous, you could use gravitational interactions to transmit information faster than light, which would violate causality, the principle that causes must precede their effects. So Einstein spent a decade, from 1905 to 1915, constructing a new theory of gravity that was consistent with relativity. The result was the general theory of relativity, one of the most beautiful and successful theories in the history of science. In general relativity, Gravity is not a force transmitted instantaneously. It is the curvature of space-time, and changes in that curvature propagate at the speed of light. Einstein's theory in a single stroke resolved the incompatibility and revealed that gravity and light, seemingly so different, are connected by the same fundamental constant. The speed of light is not just the speed of light, it is the speed of causality. It is the speed at which the universe updates its description of itself. This is the counterintuitive truth at the heart of this thought experiment. We think of light and gravity as separate things. We experience them as separate. Sunlight touches our skin, gravity holds us to the earth. They feel utterly different. But at a deep level, they share something fundamental. Both are limited by the same cosmic speed limit. Both are ways in which the universe carries information about the distribution of matter and energy from one place to another. And both, it turns out, take exactly the same time to tell the Earth that the sun is gone.
Let me offer you a thought experiment within a thought experiment to make this vivid. Imagine you are standing on a dock and you are holding a rope that extends out over a lake and is attached to a boat. If you pull the rope, the boat moves. If the boat moves toward a dangerous rock, you would pull the rope to redirect it. Now imagine the rope is not a physical rope, but a gravitational connection. If the sun were to suddenly vanish, in Newton's universe, the rope would simply disappear, instantly. The boat, meaning the Earth, would immediately be free. But in Einstein's universe, the rope is not a connection that can simply vanish. It is more like a tension carried through the medium of space-time itself. And when the sun vanishes, that tension does not disappear instantly. Instead, a disturbance travels along the rope, from the sun end toward the earth end at the speed of light. For 8 minutes, the earth is still held, the tension is still there, the disturbance is still traveling, and then it arrives, and the rope goes slack. This image, imperfect as all images are when used to describe physics, captures something true about general relativity. Space-time is a medium. It is not empty nothingness. It has properties. It can be curved. It can carry waves. It responds to the presence and motion of matter and energy. And when something changes, it takes time for that change to propagate. The universe does not have a central clock that everything updates simultaneously. It has a web of causal connections, and those connections all have the same maximum speed. The confirmation of gravitational waves by LIGO in 2015 and the subsequent detections by LIGO, Virgo, and Cagra have moved this from theoretical prediction to observed reality. We have heard, in a sense, the universe speaking through the medium of space-time. The instruments detected waves created by events that happened hundreds of millions of light-years away. The waves that arrived at our detectors carried information about those cataclysmic events, encoded in the geometry of space-time itself. Every detection is a reminder that we live inside a universe that is dynamic, that is communicating with itself constantly through both electromagnetic radiation and gravitational waves, and that we are finally, after billions of years of life on Earth, building the instruments to listen. I want to spend a moment on something that rarely comes up in discussions of this thought experiment, but that I find deeply important. It concerns the nature of our relationship to the sun over time, not just the sun we know now, but the sun across the history of the solar system and into its future. We tend to think of the sun as a fixed feature of our cosmic environment. It has always been there, for as long as humanity has existed. Every culture in human history, every civilization, has organized its understanding of time and existence around the daily rising and setting of the sun. The sun is in our mythology, our religion, our science, our agriculture, our art. It is the original given, the unchallenged constant. But the sun is not eternal. It is not unchanging. It is a star, and stars have lives. They are born from collapsing clouds of gas and dust. They spend most of their lives fusing hydrogen into helium in their cores, generating the outward pressure that balances the inward pull of gravity.
And then, when their hydrogen fuel runs low, they change. They become something different. Our Sun is currently about halfway through its main sequence lifetime. It has been burning hydrogen for approximately 4.5 billion years, and it has roughly another 5 billion years before its hydrogen core is exhausted. At that point, it will expand. It will become what astronomers call a red giant, swelling outward to perhaps 100 times its current diameter. The inner planets, Mercury and Venus, will almost certainly be consumed. Whether Earth is consumed depends on details we cannot yet predict with certainty. But even if the Earth survives the expansion in a technical sense, it will be a scorched, unrecognizable world, entirely inhospitable to any form of life as we know it. After the red giant phase, the Sun will shed its outer layers, releasing them into space as what astronomers beautifully call a planetary nebula, a glowing shell of gas that will expand and disperse into the interstellar medium. What remains at the center will be a white dwarf, a dense remnant about the size of the Earth, made primarily of carbon and oxygen, slowly cooling over billions of years. The material that was once our Sun will have been returned to the cosmos to eventually become part of new clouds of gas, new star-forming regions, new planetary systems, new possibilities. The atoms in your body have been through processes like this before. The carbon, oxygen, nitrogen, calcium, iron in your body were forged in the interiors of stars that lived and died long before the Sun was born. You are made of stellar material. Every human being is a collection of atomic nuclei assembled in supernovae and stellar furnaces across billions of years of cosmic history. We are not observers of the cosmos from the outside. We are expressions of the cosmos, shaped by its processes, built from its materials, following its laws. And the Sun is not our master or our creator in any mystical sense. It is our nearest star, our source of energy, our gravitational anchor. It is a sibling in the great family of stellar objects that fills the Milky Way. There is a profound shift in perspective that comes from understanding this. When you think of the Sun as one star among several hundred billion in our galaxy alone, and when you think of our galaxy as one among hundreds of billions of galaxies in the observable universe, the specific configuration of our solar system becomes something remarkable precisely because of how contingent it is. The fact that a star of exactly this mass and composition, formed in exactly this location in the galaxy, with exactly this collection of planets, in exactly these orbits, with exactly this moon, producing exactly the gravitational and electromagnetic environment that allowed exactly these kinds of molecules to form and self-replicate and eventually become conscious beings capable of asking, what if the Sun suddenly disappeared, is not something that was guaranteed. It was not inevitable. It is, by any reasonable accounting, extraordinarily improbable. And yet, here we are, asking the question, understanding the answer, marveling at the physics. Let me turn now to something that this thought experiment clarifies about the concept of the present moment, because I think it is one of the most philosophically significant implications of what we have discussed. When you look at the Sun, you see it as it was 8 minutes ago. When you look at the Moon, you see it as it was about 1¼ seconds ago. When you look at the Andromeda Galaxy, the nearest major galaxy to our own, you see it as it was about 2.5 million years ago. The light reaching your eyes left Andromeda before modern humans existed. And when astronomers observe quasars at the edge of the observable universe, they are seeing them as they were 10 or 12 billion years ago, when the universe was young and dense and wildly different from what it is today.
There is no observation that gives you the universe as it is right now. There is no way to see the cosmos in real time. Every view is a view into the past, and the further you look, the further back you see. The observable universe is, in a sense, a sphere of past moments, arranged concentrically around us, with the oldest moments at the outer edges and the more recent ones closer in. We sit at the center of our own observable past. Other observers, elsewhere in the universe, sit at the center of their own observable past. And because the universe has been expanding since the beginning, the regions accessible to different observers are different. No two observers, separated by a significant distance, see the same universe. This is deeply counterintuitive. We have an intuition that there is a shared present, a single moment called now, that encompasses everything that exists simultaneously. But physics does not support this intuition. Einstein's special relativity showed that simultaneity is relative. Two events that appear simultaneous to one observer may appear sequential to another observer, moving relative to the first. There is no absolute now. There is only a network of causal relationships connected at the speed of light and the local present of each observer. When we speak of what is happening right now in a distant galaxy, we are using language that carries more certainty than the physics actually allows. The sun's disappearance in our thought experiment makes this vivid. For 8 minutes, there is a genuine sense in which the sun has disappeared in some reference frame and still exists in another. The Earth's reference frame still contains the sun in the sense that it is still receiving light and still feeling its gravitational influence. The sun's former location contains nothing. These two regions of spacetime are not yet causally connected regarding the sun's disappearance. The information has not had time to bridge the gap. And so, in a very precise physical sense, the sun both has and has not disappeared, depending on where in spacetime you are asking the question. The concept of the sun's existence becomes relative to position, not in a vague philosophical sense, but in the precise, measurable sense of physics. This should make us humble about the concept of objective reality. Not in a way that denies reality, not in a way that suggests everything is subjective and nothing can be known, but in a way that recognizes that reality as experienced by any observer is always partial, always delayed, always local. The universe we know is not the universe as it is. It is the universe as it was, seen from here, filtered through the instruments and senses available to us. And that is an extraordinary thing to sit with. Let us now consider a related question that often arises in the context of this thought experiment. Why does the speed of gravity equal the speed of light? Is this a coincidence? Could it have been different? Could there be a universe in which gravity propagated faster than light? This question takes us to the edge of what current physics can answer, and I think it is worth being honest about that edge. The equality of the two speeds is a deep feature of general relativity. In Einstein's theory, both gravitational waves and electromagnetic waves, including light, are disturbances that propagate through spacetime itself. The speed at which they propagate is determined by the same fundamental properties of spacetime, specifically what physicists call the permittivity and permeability of the vacuum, or equivalently, the relationship between space and time encoded in the metric of spacetime. Because both types of waves propagate through the same medium according to the same underlying equations, they travel at the same speed. Whether this had to be the case, whether a logically consistent universe could have different speeds for different types of signals, is a question that takes us into the territory of theoretical physics that remains active and unresolved. There are theoretical frameworks in which the speed of gravitational waves and the speed of light might differ slightly, and precision measurements from events like the detection of gravitational waves and gamma rays from colliding neutron stars have placed extraordinarily tight constraints on any difference. The gravitational waves and the gamma-ray burst from the neutron star collision observed in 2017 arrived within seconds of each other, after traveling a distance of about 130 million light-years. This constrains any difference in their speeds to less than 1 part in 10 to the 15th. They are, to any measurement we can make, identical. This observation was itself one of the most significant scientific events in recent decades.
It confirmed simultaneously the gravitational wave prediction of general relativity, the association of certain gamma-ray bursts with neutron-star mergers, and the extraordinary equality of the speeds of gravitational and electromagnetic waves. In one event, physics became richer and more precise than it had been before. This is the nature of science, not a collection of facts memorized from textbooks, but a living process of observation, prediction, testing, and refinement conducted by curious human beings using the most precise instruments we have ever built. I want to return near the end of this exploration to the human dimension, because all of this physics, as beautiful and precise as it is, exists in a context. The context of conscious beings who are themselves made of the same matter the sun is made of, trying to understand the universe that made them. There is something almost circular about it. The sun fuses hydrogen into helium, releases energy, bathes the earth in light, powers photosynthesis, supports food chains, supports animal life, supports primate evolution, supports human civilization, supports the development of physics, which eventually explains the sun. We are the universe understanding itself. The sun created the conditions in which creatures capable of explaining the sun could arise. When I contemplate the 8 minutes of delay in our thought experiment, I find myself moved not by the destruction it implies, but by what it reveals about presence. Every moment that you experience sunlight is a moment of connection with something 8 minutes distant. The photon that warms your face departed the sun's surface before you began reading this. It crossed 150 million kilometers of vacuum without interacting with anything, and then it found you. In a universe where most of the vast majority of space is empty, that photon finding you is itself a kind of miracle, not a supernatural miracle, a physical one. A consequence of geometry and probability and the extraordinary size of the sun, which releases so many photons per second that even across that immense distance enough arrive at every square meter of Earth's surface to sustain life. The Earth receives only about 1/2 billionths of the total light the sun emits. The rest goes out into space in all directions, warming nothing, falling on no planet, received by nothing with the capacity to appreciate it. And yet that 1/2 billionth is enough, more than enough. The amount of solar energy hitting the Earth's surface every hour is greater than the entire energy consumption of human civilization in a year. We sit in a bath of energy so abundant that we have barely begun to use it. The sun is, in this sense, absurdly generous to us, extravagantly, wastefully generous, in the way that only a star can be. If the sun were to disappear, we would lose not just warmth and light and gravity, we would lose that extravagant generosity. We would lose the source from which all food ultimately derives, from which all weather ultimately derives, from which all ocean currents ultimately derive, from which all the chemical energy stored in fossil fuels ultimately derives. We would lose the biological clock that every living thing on Earth has evolved around, the circadian rhythms that govern sleep and waking, the seasonal cycles that govern reproduction and migration, and the behavior of ecosystems. We would lose the driver of the carbon cycle, the water cycle, the nitrogen cycle, the entire metabolism of the Earth's surface, a system of almost incomprehensible complexity and interdependence, runs on sunlight. Remove it, and the metabolism stops. But I want to end not with catastrophe, but with wonder, because I think the most important thing this thought experiment teaches is not about destruction. It is about connection, about how deeply and completely our existence is embedded in the existence of a particular star. We did not choose the sun. We did not negotiate the terms of our relationship with it. We evolved into that relationship over billions of years, every organism on this planet shaped by the specific character of this particular star's light. The peak wavelengths of sunlight, the specific colors that dominate the solar spectrum, are the wavelengths that evolution has calibrated our eyes to see. Human vision is the sun's light made into perception. Our biology is a negotiation with a star. And the star does not know we are here. It does not care. It simply burns, as it has burned for 4.5 billion years, following the laws of physics, indifferent to the life that has arisen in its gravitational embrace. There is no malice in the sun's indifference. There is no comfort in it either. There is simply the universe operating as it does, by laws that do not make exceptions and do not recognize significance. And within that vast, indifferent, lawful universe, something improbable happened. Life emerged. Consciousness emerged. We emerged. And we turned our eyes to the sky, and we wondered, and we asked, and we figured out the answer. The sun will not suddenly disappear. General relativity and thermodynamics and stellar physics give us no mechanism by which it could. But the thought experiment exists because we can ask it, because our minds are capable of stepping outside the given and asking, what if? That capacity to imagine a different universe and then use the laws of this one to trace its consequences is itself one of the most extraordinary things the universe has produced. It is physics done in the imagination, tested against mathematics, confirmed against observation, and it produces answers that are stranger and richer than the question deserved. When you next step outside on a clear day and the sunlight falls on your face, you might carry with you the knowledge that you are feeling something that left a star 8 minutes ago, that the warmth you feel is fusion energy released in the core of the sun and then carried across 150 million kilometers of empty space to reach you specifically at this moment, at this particular point in your life. And that the gravity holding you to the earth, which feels so simple and obvious and inevitable, is actually a curvature in the fabric of space-time, created by the mass of the earth you stand on and tuned by the mass of the sun above you, and that this curvature travels and responds and propagates at the speed of light, just like the photons making the day bright. Everything that seems ordinary is extraordinary when you understand it deeply enough. The sun is not background, it is the condition of your existence. And the universe, in its vast, patient, lawful way, is telling you that by making the connection travel at the speed of light, by encoding the relationship between cause and effect into the very structure of space-time, and by ensuring that when something changes, you have exactly 8 minutes to notice it before the change arrives. 8 minutes. In the cosmic scale of time, 8 minutes is nothing, less than nothing, a rounding error. But in the scale of a human life, 8 minutes is time enough to step outside and feel the warmth of a star on your face. Time enough to understand what you are feeling. Time enough, perhaps, to be grateful for the extraordinary and improbable arrangement that makes such understanding possible. The universe gave us the sun, and the sun, across 4.5 billion years, gave us everything else.